Alright, welcome back to class, and in this video we'll be diving into the 555 timer IC. So what is a 555 timer? Before we dive into that, let's first start with what is an IC. So an IC stands for integrated circuit. An IC stands for integrated circuit. It means that in a single package there's actually a circuit there consisting of transistors, resistors, diodes, capacitors, and many more components in a single package. A simple IC should contain at least maybe a simple IC can contain anywhere from 10 transistors to 120 transistors, while a microprocessor IC can contain millions of transistors in a single package. That's how it is. Now, when you see a IC, how do you recognize them? My advice is simple. Anything that is more than 3 pin, that has more than 3 pin, just Google search the name you see on it. So for example, this is NE555. You can Google search it, then you will know whether it's an IC or something else. If it's a 3-pin component, it may be an IC, it may not be. So for example, the LM7805 is a voltage regulator IC, but the TP41 is a transistor, yet the two of them are 3-pin and the same package. So that's why I said that if it is 3-pin, at least 3-pin, and you are not sure what it is, Google search it. Or if it is becoming 4-pin, you can also Google search it. Sometimes 4-pin can mean a bridge rectifier diode, maybe a bridge rectifier diode that's inside. But when it becomes 5-pin, it's an IC. It's definitely an integrated circuit. So 3-pin, if you are not sure, Google search it. 4-pin, if you are not sure, Google search it. But 5-pin is an IC. And the way you will know is that you should love your search engine. Use your search engine a lot. Alright, so for this IC, this package is called double inline package, DIL. Double inline. So that means you will see some pins here and you see some pins at the other side there. So if you count the number of pins for any 555, it's 1, 2, 3, 4. There are pins here, 4 pins also here, 5, 6, 7, 8. So you call this one 8 DIL, 8-pin DIL. So that means we have 4 on this side and 4 on the other side. How do you know which one is pin 1? So pin 1 starts from here. So it starts from where this dot is, the pin that is closest to this dot. Or if you want to consider this notch here, that will be the pin that is leftward to this notch here. So that is the pin 1. Now let's continue. What is the 555 IC? It's a monolithic integrated circuit renowned for generating precise timing signal. Where at your level, we can call it precise timing signal. You know, for example, in the RC delay circuits that we did earlier, you can't really control how long the delay should be and all. You just assume, and you can make assumptions. While there are calculations that can help you streamline your assumption to a near accuracy, this IC does better. So, and the design is simple and is sufficient to power everything from LED displays to some complex management system. So I told you earlier that inside this IC you have transistors, diode, capacitors, and as many as possible. So this is the internal diagram of this IC, internal circuit diagram of this IC, and you have all the components that are needed embedded into that single IC. So operations, what are the basic operations you can use the 555 for? You can use it as a monostable, like a timer. Once you press the start or a trigger button or a trigger switch, it starts counting until it times out. That's like a timer function. Then you have the bistable. The bistable, you can call it like a toggle switch, on or off. on or off. Now, if you remember, there was this temperature controlled fan circuit that we made earlier that it was coming on gradually. You can use a 555 IC to cut off that gradual turning on approach. So with 555, you can make it ensure that it's either fully on, or fully off once the trigger is applied. Do you see that? Okay, let's continue. And then you have the astable mode. In astable mode, this is the astable mode. In astable mode, you can make it generate a particular oscillation, square wave oscillation with adjustable frequency and duty cycle. And if you combine more than one any 555 timer together, you can generate different kinds of waveform, different kind of modulation and tone. For example, if you've heard of this alarm circuit that's saying wow, 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 you can use your 555 timer to generate it. Yes, you can do that. Alright, having said that, what are the applications you can build something you can build with your 555 timer? You can build a smart lighting system such that maybe, for example, you have a night reading pattern, so that you want to just let the light turn on for 30 minutes once you press the switch, and you want the light to just be on for around 30 minutes, and after 30 minutes it goes off automatically by itself. You can use your 555 to do that. You can use it for water boiling, for example, boiling alarm. You want to boil your egg boiler. I've had some projects like egg boiler. So your egg is not meant to boil for more than 10 minutes in the boiling water. So you can use 555 timer to create that timing such that after 10 minutes it sounds an alarm. You see that? You can use it for a touch switch, maybe for your door, for your cabinets and all at the DIY level. Alright, having said that, let's go ahead and build something with 555 timer. Let's simulate something with 555 timer. The first thing I would like us to create is the monostable. So I'll bring it here, rotate it. So don't forget, this is pin 1, then pin 2, pin 3, pin 4, pin 5, pin 6, pin 7, pin 8. Let's zoom in this image so you have more view of what we are doing. Pin 1 is the ground, pin 2 is the trigger, pin 3 is the output, pin 4 is the reset, pin 5 is the control voltage, pin 6 is the threshold, pin 7 is the discharge, and pin 8 is the power. Every IC has its own peculiarity of how it is to be used. Let me repeat that again. Every IC has its own peculiarity of how it should be used. So to help us to use this 555 timer as a one-shot or a monostable circuit, this is what we're going to do. Let me just show you how. If you want to use any IC, we are going to go and browse for the data sheets. So let's search for the data sheet. So in here, I'm going to press NE555 and press enter. Now you see it brought me different things. You can already see some circuit diagrams and images. All of this you are free to practice it, right? You are free, definitely free to practice it. So I'm just going to use the data sheet. So I'm going to use this data sheet. So look at this. You have all of these timing features, timing from microseconds to hours, astable or monostable operation, adjustable duty cycle, TTL compatible, output can sync or source up to 200 milliampere, and all of that. You have applications, pulse shaping circuit, missing pulse detector, pulse wire, and all of that. And if you can read. You should actually start getting yourself familiar with reading data sheets. You should start doing that. Alright, we are going to the applications page. So you see the pin outline. Pin 1 is the ground, pin 2 is the trigger, output, reset, control voltage, threshold, discharge, and VCC. You have another package like this, and this is the pin functions. Okay, let's talk about the pin functions. Pin 1, which is the GND, is the ground. That is settled. Pin 2 is the trigger, which is an input pin, and what it does is that it is the start of the timing input. Do you get that? The trigger voltage is less than half of control voltage. It sets its output high and discharge open. Don't worry, we're going to explain this. Then the threshold is the end of timing inputs. And when the threshold is greater than control voltage, it sets output low and discharge low. Right. Pin 3 is the output, high current timer output signal. Pin 4 is reset, active low reset input, forces output and discharge low. That's that. Pin 5 is the control voltage, controls comparator thresholds. Right. Pin 6 is the threshold. I've already mentioned that. Pin 7 is the discharge. Open collector, output to discharge timing capacitor. Okay, if you want to understand how these things work, you can actually read up the data sheet in details. So we are going to the application page. Coming. Alright, so they are trying to explain the internal circuitry of how it works. Yes, so this is the first one. Fixture description, monostable operation, figure 6.2 shows how to connect any of these timers for monostable operation. If the output is low, application of a negative going pulse the trigger sets the flip-flop and drive the output higher and turns Q1 like that. So let's draw this circuit in our simulation. So keep this circuit in mind. We're going to use it in our simulation soon. So we just take it one after the other. Pin 1 is the ground which connects to our battery. So let's go and do that. So I'm going to bring in my battery here, or let's just use our power supply. Let's not use battery again. And pin 1 goes, let's make it color black. Pin 1 goes to ground. Connected. What does pin 2, which is the trigger, what does it do? How is it connected? The trigger is the input. So it's not connected to anything yet. So let's leave it for now. Pin 3 is where you connect your output, your light emitting diode. So let's connect something. Let's connect our light emitting diode there. Of course, we are going to do it through a resistor. So we need a resistor. Let's put it like this. And a light emitting diode. So it's going to go like this. Let's change that color. And it's connected to the positive supply. So that's pin 3. Let's see what's pin 4. How do we connect to pin 4? Pin 4 is the reset. Look at it. It's connected to the positive line to VCC. And VCC is pin 8. So pin 4 and pin 8 are connected together. So let's draw this circuit. Let's draw another power line from here. and we are taking it all the way to pin 8. Right, then we saw that pin 4 is connected to pin 8. Hope you are following. If it's getting complex, you can slow down and master what we are doing properly. Okay, so pin 4 is connected to pin 8 in that manner. Then pin 5, is it connected to anything? Pin 5 is connected via a capacitor to ground. Okay, so we're just going to do the same thing too. So we need a capacitor. In most cases, I don't get to put the capacitor there in my own simulations or my own circuits. I don't get to put the capacitor, but let's put it. Let's use the color pink we're using before, or let's use color turquoise. You're at liberty to choose any color, please. The color is just to bring a little difference, and the negative goes to ground. For that, I would like to use color black. Okay, let's just draw from there. Okay, that's done. The next pin is threshold. The threshold, and this is discharge. So what is the threshold connected to? So the threshold and discharge are connected together. Right? Let's first do that. The threshold and discharge are connected together. So let's do that first. Then they are now connected via a resistor to the positive line and via a capacitor to the negative line. So via a resistor to the positive line, so I need another resistor. Okay, since I already have capacitor, let's start a capacitor first. Via a capacitor to the negative line, so I'm going to connect this to this capacitor. The other end of this capacitor goes to ground. Then via a resistor. To the positive line. Okay, so that's the circuit there. Let's change this to turquoise for uniformity. So that's the circuit. Now, what are the values that are necessary to operate this? For this one, if you are using 5 volt supply, your 220 volts will still be okay. Your 220 ohms, 220 ohms will still be okay. For this one, it's recommended 1 UF is okay, or 10 microfarad, 16 volt is okay. But now, what are the values of this resistor and this resistor? Let's see the data sheets. Now, in the data sheets, this resistor, that first resistor is called RA and this one is called C. Now, monostable operation is initiated when the trigger voltage, let's zoom in, when the trigger voltage is less than the trigger threshold. Sorry about that. After being initiated, the sequence ends only if the trigger is high for at least 10 microseconds before the end of the time interval. Okay, when the trigger is grounded, the comparator is just trying to explain the theory behind how it works. So let's just fast forward. As a result of the threshold level and saturation voltage of Q1, the output pulse, this is what we are looking for. The output pulse duration is approximately 1.1 multiplied by RA times C. Do you get that? So the approximate pulse duration, the length of that timing, is given by 1.1 multiplied by RC. Do you get? Figure 6.4 is a plot of the time constant for various value of RA and C. So for example, if we choose RA to be 1 kilo ohms and C is equal to 0.1 microfarad, the time we will get will be around 10 to the power minus 4. That's too short. We will not notice anything happened. Let's go to the high end for around this 1 seconds. So if we choose our R to be 10 mega ohms, are you following? And the capacitance to be 1 microfarad, we will get 10 seconds. If we choose it to be 1 mega ohms and the capacitance to be 0.1 microfarad, we will get 1 seconds. So we can play around with this, or we can just calculate our own value. So let's go ahead and just do some calculation. Let's do some calculation. Assuming we want a timer that will delay for 10 seconds. See the time t, we want it to just be for 10 seconds. And now we want to calculate the value of our R and C. I will prefer that we find the value of R. The value of R is more flexible than the value of capacitors. So let's set our capacitor value to be 10 microfarad. That's our C. So we need to find the value of R. If the formula T is given by 1.1 RC, the value of R will be given by T over 1.1 multiplied by C. And that will be equal to our T, which is 10 seconds. Always use your T in seconds when you are calculating. Multiply by 1.1 multiplied by 10 microfarad. That's 10 times 10 to the power minus 6. So let's calculate this. What will it give us? That will give me 0.000011. That's 10 over 0.000011. So by the time we do that division, 10 divided by 0.0011, I have 909 comma 090.1 ohms, right? Okay, so these are approximately equal to, now there is 91 kilo ohms resistor, 9.1, 91. To know the values of resistor that are commonly available, you can search for E24 resistor table. E24 resistor table. So this is approximately equal to 910 kilo ohms. Or if you are not too critical about time, you can just go ahead and use 1 mega ohms resistor. We are going to use the two, and you discover that you won't really find too much difference about the output. So the value of our resistor is 1 mega ohms, and the value of our capacitor is 10 UF. The value of our resistor is 1 mega ohms, and the value of our capacitor is 10. 1 mega ohms and 10 UF. So let's go ahead and implement that in our circuits. So this is 1 mega ohms and this is 10 UF. So having done that, let's start this simulation. Now, good. The device did not come on until around 10 seconds. Did you notice that? Let's stop it. From our calculation, we want a timer that turns on the LED or light emitting diode in 10 seconds. We want a 10 seconds delay, right, before it turns on. And from our calculation, we selected the 1 mega ohm resistor and the 10 microfarad capacitor. So let's go back to the simulation and to see whether what we did was correct. So when I start the simulation, see the time here and see the light emitting diode. So 3 seconds now, 5 seconds, 6 seconds, 7, 8, 9, 10, 11, and the light is on. Do you see that? Now, when you compare this with the transistor-based timer, in the transistor-based timer, the light was coming on gradually or going off gradually. That's not what we want. In this case, once it is time, it turns off, or it turns on, or once it is time, it turns off. Do you get that? All right. Okay, so in this case, this circuit turns on the LED after 10 seconds. What if we want it to actually turn off the LED? Very simple. This is what we are going to do. Instead of driving this light emitting diode directly from here, let's delete it here. This LED connects to here actually. Connects to the power here. Let's just make it look like this. Let's rotate this. So I'm just going to connect this one here. That simplifies that. Okay, so I'm going to take the actually, you know what, we didn't connect pin 2 to anything and yet it worked. That is not right. Before we go ahead and do that, in a real life scenario, you may experience issues. So normally you should connect pin 2 via a resistor to the positive power line. This is so that the device should not trigger until you trigger it, right? If you want to trigger it automatically, I will show you another way to do that without leaving this pin floating. If you leave it floating, it means that anything can trigger it. Anything can happen that will just trigger on your circuit, and that's not what you want, right? So if we start simulation now, I don't expect this LED to come on at all because there's no trigger. So let's see if it comes on. Oh, it came on. All right. But now we can't trigger it back again. We can't trigger it back. So this is what we are going to do now to trigger it to make the timing start again. Make the timing start again. So I'm going to stop this and add a button switch. I will add a button switch between pin 2 and ground. So then it goes to ground. Good. So let's start the simulation. Let's see. After 10 seconds, the light comes on. That's the first delay. If I want the delay to happen again, right? If I want the delay again, I will press this button and the light goes off. And it will come on again in the next 10 seconds. Do you see that? So let's wait. That's around 29 seconds. It will come on and it's on back. Do you see that? So that's what we mean by the trigger. So this trigger can be anything. It's not necessarily a button switch. But imagine if you are actually creating a night reading lamp that you want it to be on for like maybe 30 minutes, then it goes off, right? So you can just use this method once you press the button. Now, but in this case, the light is always on, and when I press the button, the light goes off. What if I want to invert that characteristics? So what we can do, let's first experiment like this. Let's stop this. Let's remove this from here. Remove this in this manner. I will shift this one a little bit to this side. And shift this one too. Okay, and don't forget the C connect to the positive line. Then the output. Okay, I've not connected this. So let's connect the output to ground instead. And let's see if we have the characteristics that we are looking for. I need a resistor. And I need a light emitting diode. Okay, so if we do this, will it behave the way we want it to behave? That is, the light comes on and stays on, then goes off after 10 seconds. That's what we want, right? That's what we want. So if I press the button again, light comes on again and stays on and goes off after 10 seconds. Goes off after 10 seconds. Do you see that? Let's do it again. Light comes on and goes off after 10 seconds. So you can increase the length of timing by increasing the value of this resistor and this capacitor. So this is a basic timer circuit. Do you get it? All right, that's beautiful. I'm going to stop the video here, and we are going to do the oscillation circuits, that is the astable, in another video, and the bistable in another video. Thank you.